let's find out how we can solve the structures just using just spectrum alone. I mean, of course, you got to know how many carbons in here, so we can give you the formula, the molecular formula there. Or we could basically give you the mass spectrum. The mass spectrum gives you the total number of mass, so you could figure out how many carbons and hydrogens are there from that, but that would make it even more difficult. So let's look at this question. That question has a molecular formula given here. It's a C9H10 and just the one oxygen. And then it has a peaks here. So we need to find out, we need to figure out what is the structure of the organic molecule that gives this spectrum out. So for that, there are some useful things you can do, which is it's called the degree of substitutions. I didn't have this on this slide. The degree of unsaturations is actually, figuring out how much unsaturation in the molecule. That's basically what it's measuring, and it can be done by this formula. Degree of unsaturation is the number of the carbon. You gotta subtract the number of the hydrogen, and then if there's any halogen, you can also subtract number of the halogen too. But if there's any number of nitrogen, you basically add the number of the nitrogen and plus one. So that is a degree of unsaturation. If you plug this formula into that, you can find out what's the degree of unsaturation of the molecule, what that means, how many double bonds. It might be the cyclic structure too, because being a cyclic structures raise the one degree of unsaturations. So if we do that with this formula, C9H10O1, by the way, oxygen doesn't do anything from the degree of unsaturation. That's why it doesn't appear in the formula. So 9 carbon, right? We got 9 carbon, and then we got 10 hydrogen. So, and then we got no nitrogens, no halogen, just oxygen there. So nothing else we can do, and plus 1. So that will be 4 minus 5. That will be 4 plus 1. That will be 5. So we have a 5 degree of unsaturation, which is a pretty high, you think. But some of the degree of unsaturation actually can come from having a benzene here. You recognize there's a multiple page showing between 7 and 8, right? That must be the hydrogen on benzene. I mean, obviously, right now, we don't know how many hydrogens are there, but thankfully, this spectrum came with integral line. This integral line points out how many hydrogens might be under that aromatic peak. So we need to figure out how many hydrogens are on the benzene. But we can say that there must be a benzene. And how many degree of saturation benzene can make? It has 3 double bonds and a cyclic structures. So benzene can make up to 4 degree of unsaturations. So we got 5 degree of unsaturations, but 4 out of 5 actually came from the benzene. So we have 1 more degree of unsaturation. That could be double bonds or cyclic structures. I don't know what it is, but that's something we need to figure out. Anyway, so we know it's a benzene because of the peak between 7 and 8. And then what else is very characterizable in this spectrum? You're going to recognize this one. There's a peak between 9 and 10. And I've been telling you, if you see the peak showing up between 9 and 10, only aldehyde can make a signal at that region. So that means that you have an aldehyde. And that aldehyde must have a carbonyl. Otherwise, it wouldn't be called as an aldehyde. So that carbonyl could be the remaining 1 degree of saturation besides the benzene. So aldehyde, the carbonyl, and the benzene, we basically found all 5 degree of saturations. Anyway, what other thing could be useful from this peak? Aldehyde is just 1 hydrogen. Integral line, it went up here to there, just went up like a half step, right? So that half step increase in the integral line, that's because of the one hydrogen. So we need to find out how many steps it went up. So it's like 1, 2, like 3. I mean, I don't know, this about half step. So 1, 2, close to 3. I don't know, right? 1, 2, 3. And yeah, something like that. So it has to have a somewhat large number of hydrogens. I mean, there's no way it could be 6 because it's it has to be substituted. So I should say there should be like many hydrogen, but it could be not just 1 or 2. So you're using these numbers to figure out that 1, 2, 3, 4, maybe 5. I mean, if you try to measure it, you're going to just do that. So I think it's a 500 there, based on just rough estimation. But that's basically what you can use integration to find out how many hydrogen benzene, because of that hydrogen on the aldehyde signal has to be just 1. Now looking at this one's a triplet, 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 triplet. So what that triplet, triplet means, that's the kind of things that you need to figure out. Triplet, triplet means, this being triplet because it has how many number of additional hydrogen? 2, right? And that's a triplet because it has also 2 adjacent hydrogens. So what could potentially make this pattern is a 2 CH2 put together. Then they split each other. This makes that one triplet, that one makes this one triplet. So triplet, triplet, and this must be equally 2 hydrogen to each. And then we talked about like the half steps of 1 proton. So these are like a 1, 2, 2 hydrogen here and 2 there. So CH2, CH2. That's it, basically, I think, that's what it can code. Being next to each other, it could be triplet, triplet. So with the integrations, position of the signal, splitting pattern, we can figure out that belongs to the benzene with the 5 hydrogen. That's all the high signal here. And this must be CH2, CH2. So then we can figure out, did we find everything? We were supposed to find out 10 hydrogen. There's a 5 here, including 6, and then 2 there, 2 there. So we found all 10 hydrogen. So that's all the pieces that we could find from this. And then now what we can do, we need to put them together. So how are we going to put them together? If there's only one way to put it together, then it's easy. But if there's a different way to put it together, then you've got to be careful. Because even though you find out the right pieces, but by putting it together, you're actually giving the wrong answer. So normally, I would suggest that you make up the structures for the pieces and you double check by going backward. So from this one, let's talk about other things. Why they're in the like a 2.7 and 2.9, their chemical shifts are very similar to each other's. So what's typically appearing make the hydrogen appears between 2 and 3. So there are 2 things make things happen that way. One, hydrogen next to carbonyl or hydrogen next to the benzene, like a benzylic hydrogen. Those are the ones could happen between like 2 and 3, or I would say 2.5. But if they are kind of a beta to another electron withdrawing groups, we can shift a little further, getting close to 3. So I think there's a carbonyl is definitely one of these 2 CH2, and the benzene is next to one of these CH2. So, but that's kind of obvious because we can only connect this only one connection today because it's benzene with a 5 hydrogen, only 1 open bond. That has to connect to here, and this end has to connect to the aldehyde of the carbonyl. Then this would be the structure of giving out the spectrum. And this being a benzylic position, I'm expecting that to be 2.5 chemical shift, but also the beta position to the carbonyl. That's why you shift even further to get close to like 2.8, 2.9 regions. And this one too, by next to the double carbonyl, that should be like a 2.2 regions. But by being next in a beta to the benzene, it has a little influence. So maybe that's the one coming up for that one. So anyway, chemical shift makes sense, splitting makes sense, integration makes sense. So if you check it out, then now you can say, okay, this spectrum must be come from this molecule. So that is a task that you need to do. Right? Any questions? You mean this one? That splitting is because of CH2. These CH2 have only two hydrogen adjacent. These 5 hydrogen benzene, they are split. That's too far away. So only adjacent hydrogen, this one, these 2 hydrogens, let's make that 2 hydrogen into 3 triplets. And then these 2 hydrogen is also split by these 2 hydrogens, so they become triplet. And that one, that it's a very small coupling constant, so you don't normally see the split by the outer hand. All right, so these are actually pretty simple ones. That was a little bit more complicated, right? You see more number of signals. So let's do the bottom one down here. What is the most characterizable we can recognize here is, I mean, depends on who like to work on where, but I say 5 and 6 regions. This region belong to the double bond. Normally, you don't see anything unless you have a double bond, right? And then now we do see the peak here, 5 and 6. And then there's looks like a 4 peaks here, and then looks like a 2, just 2 and 2. But if you remember that the biennial, the splitting can be very close to each other. These 2, maybe 4, that 2 could be also 4. If you do the integral line, I mean, this one actually do the integration, and not only that, it also digitize the number of hydrogen for each signal. So 1 hydrogen, 1 hydrogen, 1 hydrogen, 4 peaks, 4 peaks, 4 peaks, and appearing in the double bond regions. What does it mean? That's a biennial. That's the one that I want you to remember, the pattern. These large splitting, these and then that large splitting, that makes that one. This one probably. I mean, yeah, that one. That one, these hydrogens are trans to this, cis to that, so makes up this one, and these 2, either of that, these 2. So we talked about, several slides back. So this is a biennial signal. So you can, if you can figure that out, that makes your problem solving easier. But you still have to figure out the rest of the molecule. We have something here that looks multiple peaks. And then it's appearing like a 4, little over 4. So very detuned region. So what could make things go over 4 is something that has to have an oxygen, right? And cannot have just one thing. It may have another thing there, because having oxygen can push up to like a 3.5, but moving it over 4 should have something else in there, like another electron withdrawing groups, or maybe the benzene. But we don't have a benzene here because of between 7 and 8, we got nothing. So no benzene. And maybe double bond. Double bond could be the one of the issue that push things up by the anisotropy. So this one is pointing out that we got the hydrogen, probably next to the oxygen. Maybe one of the substituents could be the electron withdrawing groups, or the double bonds, or the benzene. So anyway, from this piece, we can figure it out like this. And then there's a 3 hydrogen, and then it's a doublet. So 3 hydrogen being doublet, what does it mean? I mean, there's a 3 hydrogen, that means it could be CH3, right? It could be CH3. But being doublet, what does it mean? It means how many hydrogen adjacent orbit. That's basically what you have to gather it from. It can suggest 1 hydrogen in adjacent carbon. That's the only way this can be a doublet. So whatever it is, you got CH3, and then you have one step of hydrogen next to it. And then you have to say that, okay, there's another one here. I don't know what it is, but that might be a little broader than the others. It's a small. It only makes the 1 hydrogen. So that might be the hydrogen on oxygen. So that's why it's a little broader. And then that condition could be between 2 and 4, so it appears like 2.5. So it could be all hydroxyl groups. But anyway, so we kind of put all the pieces out. I mean, it has the 4 carbon, 1, 2, 3. I mean, you cannot have these all the pieces there. I mean, it looks like this carbon must be that carbon because we got two carbons from here. So we need to find the 2 more carbons of these 2, and then these kind of overlap that. One of these bonds could be OH, and the other one should be connected to that. So that's the only way we can put things together and then make up the structures. It's just 4 carbons, not too many hydrogens here, but because of this binary situation, you got multiple picturing in this double bonding regions, and the others are something that you gotta figure out by the splitting. You can see that splitting is actually giving out information once in a neighborhood. Using that, you gotta figure out pieces, and then you put the pieces together to make the whole structures. Do you think you can handle this? You have to. You have to make yourself do this. But after enough practice, you'll find out these are not too bad. It's kind of a very defective game. It's almost like you're reading those Sherlock Holmes. You're gonna find out that any evidence, and then you put it together to solve a mystery. That sometimes some people love this part. Believe me. But it's kind of fascinating how we can use this technique and put the structure together in case you guys completely unknown structures, but we still can figure it out. Anyway, so open solving. All right, this time you see here, I'm start to giving out 2 spectra together, right? And each technique is giving out different information. NMR can give you a particular structures, maybe not the whole, but it gives a structure of the molecule. IR, it can give out what functional group it has, like a carbonyl, carbon oxygen double bond. NMR cannot see the carbon oxygen double bond because it doesn't have hydrogen. But IR, it can detect. So IR could be complementary to the NMR. So now you kind of used to seeing multiple solving the structure using multiple spectra. So this one, we give the molecular formula C9H10O2, right? So when you see the molecular formula, what I want you to do, using this to figure out what's the degree 1 saturation. So yeah, that's the word the formula is. Anyway, now you know. 9 carbon, half of the hydrogens are -5, 9 minus 5. It's the same thing actually. So we got 5 degree 1 saturation here. So we got 5 degree 1 saturations. And then it's a lot, but you got 7 and 8, and there's 5 peaks here. So that says that you have the benzene. Benzene make up the 4 degree 1 saturation. So we have a 1 degree 1 saturation we still have to figure out. So this one must be the benzene with the 5 hydrogen. How come I was able to say 5 hydrogen? Because the integration was given as a number. These peaks are combining has a 5 hydrogens, right? So that's why I can say it's a benzene with the 5 hydrogens. So what is these 2? That's something that I want you to, I ask you to recognize, remember the pattern. Quartet, triplet, 2 hydrogen for the quartet, 3 hydrogen for the triplet. That is a pattern for the active group, right? We're telling this CH2 is being a quartet by the CH3. This CH3 becomes a triplet by the CH2. And then these chemical shift, they change depending on what they have next to it. But the thing is, this was over 4.3. That means this carbon must have an oxygen. There's nothing else can pull this far other than oxygens. So I should say, we can say that one, this one, there's only put you can substitute. CH3, it already made a bond, so you cannot put oxygen here. So that's a substructure coming out this here. But this does not say anything about 1 degree 1 saturation. We still need to find out. So that clue can be found from here. So these are the ions. What information can you pull out from the ion spectrum? It's depending on where you're looking at it. But I want you to look at this particular strong band coming down at the 1710. The 1710, if you have a deep signal down there, they could be anything. It could be aldehyde, it could be ketone, it could be carboxylic acid. But if it's an aldehyde, you're supposed to have a 2700, 2800 peaks, but we don't see that, so it cannot be the aldehyde. If it's a carboxylic acid, we're supposed to OHP really broad 3000 center, and we don't see that, so it cannot be carboxylic acid. And if it's an ester, it moves higher, like a 1740, 1750. If it's an amide, it moves down, like a 1660, 1650. So 1710. So I think this must be, it must be the ketone. But the thing is, you got to think about situation that carbonyl might be conjugated. Conjugated ester can fool you because the carbonyl signal may show around the regular ketone shows. So having a carbonyl here may not mean that, 1710 may not mean that it's actually ketone. This is actually conjugated ester. Ester is typically higher, like a 1730. But it can shift down by the conjugation to the double bonds or the benzene. So this is carbonyl actually as part of the carbonyl next to the benzene. That's a conjugated ester. And that's why I think these carbonyls are showing like a little over 1710 here. So I'm putting it together. We got ethyl groups here and ester, and these are benzene, and these makes all the hydrogen. So you have to figure things out this way.